Hi, I'm Dr. Keith Porter, Chief Engineer for the Institute for Catastrophic Loss Reduction. I'll speak to you today about benefit cost analysis of building houses to better resist strong winds and tornadoes. The work was sponsored by the Standards Council of Canada. This research also benefited from coordination by Dan Sandink and participation by 21 members of a stakeholder group who attended meetings and provided feedback and advice. Canada has a history of costly storms. Wind damage contributes about a quarter of the losses in those storms. For over 100 years, we've known how to design and build buildings to resist strong winds and tornadoes, but haven't done so, partly out of an untested sense that it might not be cost effective. This work aims to test that sense, considering this new standard CSA S520. It quantifies the added cost, benefit, and benefit cost ratio of complying with the standard relative to Part 9 of the National Building Code. Let me first sketch out some of our baseline information. There are generally three ways to estimate the performance of a building or a class of buildings in future disasters. If one has adequate empirical data, one performs a regression analysis of those data. If you lack sufficient empirical evidence, you can create an analytical model that works on theory. Most of what structural engineers do uses this approach. And if an analytical approach exceeds one's resources, then expert guessing sometimes has to do. Analytical approaches often work like this. You start by defining the asset at risk at a fine level of detail. You then do a hazard analysis, which here means estimating how frequently and severely the wind blows the asset. Then, in a structural analysis, you calculate member forces. Given member forces, one calculates probabilistic damage to individual components in the damage analysis. Then we estimate losses given damage, such as the cost to repair damaged building components. We can then calculate a variety of performance metrics, including the benefit cost ratio, among others. What evidence do we have for asset characteristics? In prior work, I compiled a stratified sample of 102 houses across Canada, 11 to 12 houses in each of 9 communities, ranging from small to large and east to west. The data come from Zillow and Google Earth Street View. For the hazard analysis, I drew on two sources. The Pacific Climate Impacts Consortium offers future straight-line wind hazard, that is wind pressure with 1 in 10-year and 1 in 50-year exceedance frequency. I assumed a middling shared socioeconomic pathway with 2 degrees Celsius heating. Canada has already warmed 1.2 degrees C over the 1961 to 1990 reference value, and 1.9 degrees C above 1948 to 2022, according to Environment and Climate Change Canada. So 2 degrees C of warming seems reasonable and perhaps a little low. To characterize the added hazard from tornadoes, one can draw on the Northern Tornado Project and other publications. The figure on the left shows the locations of tornadoes that struck Canada between 2019 and 2023. The figure on the right shows Dave Sills' lens-shaped idealization of a tornado footprint. We will need to know component damageability. Not what the safe loads are, but the probabilistic capacity of each of many damageable components. This bit matters. I'll show a few examples of the literature that I used for this study. Here's a photo of wind uplift tests of roofing shingles from Kuntz. Here's a table of roof sheathing damageability that was compiled by David Pravat and his colleagues in 2009 for various combinations of roof sheathing and fasteners. Here are some tests of roof-to-wall connections by Cheng in 2004. Simpson Strong Tie also offers some data. The published data of roof-to-wall connections were inadequate for our purposes, so we performed some roof-to-wall connection tests of our own with this 2-ton engine hoist. We tested the toe-nailed connections that comply with the building code and the same connections with the addition of a 6-inch truss screw like CSA S520 would require. The toe-nailed connections fail at an uplift force of 160 kilograms per connection, which 3 strong men could impose. The truss screw gives about 5 times that capacity. For the loss analysis, we can draw on a variety of authorities. Here are some sources for roof repair costs, other residential repairs, content value, living expenses, and carbon costs. That was a sample of the literature review. Now I'm going to summarize my analytical methodology. I define the asset in terms of the building components we normally use for structural analysis, with particular focus on the features that CSA S520 enhances, which are shown here. For example, roof sheathing, sheathing nails, roof framing and connections, roof to wall connections, and so on. That's the level of detail at which we define the asset. In step 2, the hazard analysis, that requires characterizing wind hazard in terms of the exceedance frequency of various wind pressures. The exceedance frequency for any value of wind pressure is the sum of the frequency of that pressure from straight line winds and from tornado winds. I use the PCIC table for straight line winds. It gives 2 points on a hazard curve. I assume a log linear relationship between the 3-second wind speed and mean exceedance frequency, and then I convert to wind pressure. For tornado hazard, I calculate the exceedance frequency of various reference pressures as a function of 4 things. 1, the tornado occurrence rate per 10,000 square kilometers. 2, the fraction of a tornado track length, that is EF0, EF1, etc. 3, the tornado footprint area, and 4, the pressure distribution across the width of the tornado. I'll skip over the math for the sake of brevity. It's just an application of the theorem of total probability. The third step is the structural analysis, where we calculate member forces conditioned on wind pressure. This is a room full of wind engineers, so I'm going to skip over the structural analysis. Suffice it to say that I use the National Building Code's prescribed equations for external and internal pressure on building components. Step 4, the damage analysis, requires characterizing the failure probability of each damageable component as a function of the force to which it's subjected. We define failure in a way that relates to repairs, such as the tear-off of roof shingles. This curve has the form we most often use for fragility functions, a log normal cumulative distribution function. Step 5 is the loss analysis. I've grayed out the equations. Briefly, it works like this. You calculate the cost to repair a component category K as a function of 3 things: the failure probability per component, the number of those components, and the unit cost per repair. We're careful about double counting, and we make some other reasonable assumptions about thresholds above which you just replace all the components, whether they're damaged or not. You sum over categories to get the total building repair cost. You normalize by building replacement cost to get what we call the damage factor. You calculate that damage factor as a function of pressure, and you call that relationship the vulnerability function. Then you apply that vulnerability function to the building, contents, additional living expenses, and carbon to get the total loss. Last, we calculate the benefit cost ratio. Once again, I've grayed out the equations. You integrate the vulnerability function and the hazard curve to get expected annualized loss, that is the long-term average annual loss from winds. You do that under both conditions: 1, compliant with the NBC, and 2, compliant with CSA S520. You calculate the present value of those future annualized losses under both conditions. The benefit is the difference between the two. The benefit cost ratio is the benefit divided by the marginal compliance cost. Okay, so what I've shown you so far is my general methodology. Now I'm going to show you the results of when I apply it to new Canadian houses. I told you I need to define a particular asset. I got one from Doug Terry Homes, a 3-bedroom, 2.5-bath house that approximately matches the average newer house from my stratified sample. I've grayed out the interior features here, but the drawings show all the details, the material, the geometry, etc. I did a quantity takeoff to calculate the cost to comply with CSA S520. I got unit costs from places like homedepot.ca. This table and pie chart show that CSA S520 adds about $3,600 to the construction cost of a house, or about $1.73 per square foot, which is consistent with findings from other sources. I used the NTP data to make this map of tornado frequency. It reflects 1,045 tornadoes in 4 years in 1 by 1 degree grid cells. The average rate is about 1.25 tornadoes per 10,000 square kilometers per year, and the maximum is about 9.5. Here are the resulting hazard curves at 50 pressure levels, those are the columns, and 680 locations, the rows. Here's an example showing the contribution to wind hazard from straight line winds and tornado winds in Fergus, Ontario, which gets about 5 tornadoes per 10,000 square kilometers per year. Here are my vulnerability functions. The solid line shows that a code-compliant house starts to fall apart when touched by 0.5 kilopascals, an EF0, and becomes a total loss around 1.2 kilopascals, about an EF1. The what-if vulnerability function just starts to rise at 2.5 kilopascals, which is a direct hit by an EF3 at its strongest. A CSA S520 compliant house can resist almost all the winds from almost all the tornadoes that strike Canada. I apply those vulnerability functions to the hazard curves that I have for the 680 places in the building code. Here's the top of that table showing benefit and benefit cost ratio. Here's a map of BCR. Any place with light blue or warmer colors, CSA S520 saves more than it costs, which is almost everywhere that most people live. On a population-weighted average basis, CSA S520 saves $6 for every $1 of added cost. I performed a sensitivity study. Each bar on this chart shows the range of the benefit cost ratio when you vary one parameter from its lowest to its highest value. The vertical line runs through the BCR when you set every parameter value to its best estimate. The parameters are sorted with the topmost bar reflecting the parameter that most strongly influences the benefit cost ratio. The weighted average benefit cost ratio only dips below 1 for the least damaging values of the internal pressure coefficient. BCR is fairly insensitive to the other uncertain parameters listed here. Some conclusions. First, I created a performance-based wind engineering analysis method to estimate the future wind vulnerability and losses to a particular house. I applied the method to an average Canadian house. In rough terrain, which is where most houses live, the average benefit cost ratio to comply with CSA S520 is about 6 to 1. The coefficient of variation is about 0.25, which means that for almost all locations, CSA S520 is cost effective. There isn't much data to validate the results, but my analysis roughly agrees with insurance claims data compiled by CatIQ. I omitted that slide here. Some limitations. First, I don't treat problems with inspection or non-compliance. Those things matter, but they're separate questions. I don't treat differences in provincial codes, just CSA S520 versus the National Building Code. I don't treat wind-driven rain and water damage. Finally, I focused on the vertical load path for manageability. I didn't treat lateral forces. Thanks very much.